The concept of space and time is considered to be of fundamental importance to an understanding of the physical universe. We often imagine outer space as the vast emptiness through which planets, stars, galaxies, and other objects travel, and the concept of time feels so natural that we often forget just how peculiar it is. Our current understanding is that both space and time are interwoven in a four-dimensional fabric known as spacetime. Thanks to the theory of quantum mechanics, we learned that space is not empty. There are particles rapidly bursting into and out of existence. It wasn't until 17th century that space and time were systematically defined. In 1687, Isaac Newton publishes his Principia, which, according to Brian Greene, is perhaps the single most important scientific treatise of all time, forever changing our understanding of the universe. Isaac Newton first articulated a definition on the meaning of space and the meaning of time, and the reason is when Newton was trying to work out laws of motion, he found something very interesting. He said space is an absolute unchanging arena extending throughout the cosmos, eternal static. It provides the background stage on which the events of the universe take place, and similarly he gave a definition for time. Time, according to Newton, is universal. It flows in equal intervals. You use the word equally from moment to moment regardless of whether you're on Mars, Venus, another galaxy. Time is ticked off by a universal cosmic clock that's somewhere out there in the universe, relentlessly ticking second after second after second. The equations that followed from that way of thinking about space and time really work if you use the equations to plot the motions of the planets or the Earth. They really are borne out by your observations. If you use these equations, moreover, in a more terrestrial setting, you gave Newton a rock, and he threw the rock into the air, you could make use of his equations to predict where the rock will land, and indeed if you do the mathematics correctly it works. It does predict where the rock will, and in fact even our space program, even when we go more high-tech, we try to launch a rocket to rendezvous with the moon or any of Mars or the other planets. NASA makes use of the equations that are based on this framework. Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. Newton's views on spacetime and motion dominated physics from the 17th century until the advent of the theory of relativity in the 20th century. In 1905, Einstein published his theory of special relativity, which showed that space and time were interwoven as a single structure he dubbed spacetime. Einstein was deeply disturbed by Newton's conception of space and time, and it set him out to try to understand space and time more deeply, and he felt that space and time must participate in the universe in a more intricate, a more intertwined, a deeper way, if indeed they were real. So Einstein thought about this for a long time, and by 1915 he cracked it. He realized the role of space and time in the universe because he realized that they are the medium that communicates the force of gravity. Albert Einstein revolutionized our understanding of gravity and laid the foundation for the many scientific and technological breakthroughs that came after him. In November of 1915, Einstein made one of the most profound intellectual breakthroughs in the history of physics when he developed the full implications of his ideas on gravitation into his general theory of relativity, departing from Isaac Newton's conception of gravity as a force transmitted instantaneously over distances. Einstein positioned that gravity operated as less of a force and more of a field which distorted space and time around massive objects. Thanks to Einstein's general relativity theory, we can describe gravity by attributing it to the curvature of spacetime that occurs in the presence of massive bodies. The stronger the gravity, the more spacetime curves, and the slower time itself proceeds. Time goes faster the farther away you are from the Earth's surface compared to the time on the surface of the Earth. This effect is known as gravitational time dilation. For example, if you climb on top of a skyscraper, time passes nanoseconds faster for you than for someone on the ground now because the effect is so small you will never notice the time difference. However, the time dilation due to Earth's gravity is significant enough that it makes, for example, GPS satellites adjust their internal clocks to pinpoint the location of the receiver in the ground. The accuracy of GPS positioning depends on precision time measurements of billionths of a second to achieve such timing precision. However, relativity must be considered. Special relativity shows that if we place a clock on a satellite and compare its recorded time to an identical clock in our rest frame on Earth, the satellite's clock will appear to be running behind. For GPS satellites, this difference amounts to about 7 microseconds per day. On the other hand, general relativity shows that those same clocks will tick 45 microseconds per day faster. The combined effect of relativity is that the satellite's clocks tick faster by about 38 microseconds each day. That sounds like a tiny amount. What difference could that make? Well, unless these relativistic effects are accounted for, the errors would accumulate at about 10 kilometers per day, and that new restaurant you wanted to try it would not be anywhere near where the GPS thought it should be. These effects would be far greater if You are traveling at close to the speed of light, or if you happen to find yourself in an area of extreme gravity such as a black hole is a region of spacetime where gravity is so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it if space is real and if it can respond just the way any more familiar object can be affected and respond, then it is subject. Space is subject to the laws of the universe, in particular a body of law known as quantum physics, and when you apply quantum physics to the fabric of space you run into some very deep problem to describe the gravitational field of a black hole in the physical quantities such as the space-time curvature which diverge at the center of the black hole. We need a theory that goes beyond general relativity into the quantum mechanics. Such a theory should allow the description to be extended closer to the center and might even allow an understanding of physics at the center of a black hole. No theory has yet proven successful in describing the general situation where the dynamics of matter molded with quantum mechanics affect the curvature of spacetime. A conceptual difficulty in combining quantum mechanics with general relativity arises from the contrasting role of time within these two frameworks, because in quantum theories time acts as an independent background through which states evolve. As a particle travels, it explores every possible path, and what we observe is a melding of them all. There are many proposed theories that attempt to explain what gravity is. String theory and loop quantum gravity are the most popular among these theories. When we do our analysis, like when we do our quantum mechanical analysis, we typically focus on analyzing the properties of a small number of particles, or if we're talking about universes, we model the universe as a very homogeneous structure so that we don't have to analyze all of the intricate details simply because we can't, at our current level of understanding, do that. So that's where we've gotten in our search to understand the deep laws. All of these ideas are emerging from us following in the tradition laid down by the greats, by Newton, by Maxwell, by Einstein, where they showed us that mathematical calculations can be a potent guide, a sure-footed guide, a gateway, if you will, into realms that we have not yet been able to probe experimentally. Currently, there is still no complete and consistent quantum theory of gravity, and the candidate models still need to overcome major formal and conceptual problems. They also face the common problem that as yet there is no way to put quantum gravity predictions into experimental tests, although there is hope for this to change as future data from cosmological observations and particle physics experiments becomes available. Thanks for watching. Did you like this video? Then show your support by liking, subscribing, and ringing the bell to never miss videos like this.